good friends and dear students, it gives me immense pleasure to be here again for my course Flight Mechanics. This course is related to the aircraft performance for 4th semester students of Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad, India. Today my topic is most economical climb performance. As you know that we have discussed about basics of aircraft performance, different phases which starts from takeoff, climb, cruise, descent, loiter and the landing. As of now, we have covered the first module in which we have done about basics of lift, drag, coefficient of lift, drag polar relation between drag and the lift, induced drag, parasite drag. Also we have studied about the atmosphere. Then we have done about cruise performance, in that thrust required, power required, thrust available, power available, maximum thrust velocity, minimum drag velocity, maximum velocity. So many things we have already covered. Last few classes I have discussed about climb. Climb, if it is aircraft is from the runway, it is straight. It has to make nose up. It is called the flight path angle, gamma, and it is flying like this. It is called the climb. In the climb, we have seen the effect of weight, effect of drag. So this sine gamma is equal to PA minus PR by gamma. That is the PA minus PR. PA is a power required. PR means power required divided by W, and the difference between power available and the power required is called the power excess. And as much we have the excess power, aircraft climb will be accordingly. So to have the maximum climb, aircraft should operate in a certain velocity. That velocity is very important, in which you have the minimum thrust required. So these things we have already covered, and I am Dr. Yagya Dutta Dwivedhi, professor from Institute of Aeronautical Engineering, Hyderabad. My today's topic, I am going to take forces acting during the climb, then most economical climb flight, time to climb, fuel needed to climb, distance travel during the climb, ground effect. These topics I am going to take, and descent flight. This I will be trying to cover in today's class. So if you see here, introduction to economical climb of airplane. So to have the economical, just we should have a least fuel consumption. So if you see here, this is the velocity and this is the P or the T. So mostly your aircraft should go like this. So if you are flying at the minimum drag velocity, it is the TR, and here we have the drag. So if you are flying your aircraft in this velocity, that is V at minimum drag. This is the velocity at which if you fly, your thrust required is minimum. So you can use the most economical velocity is this. So there are generally 4 types of climb. That is the best angle climb, best rate climb, cruise climb, and the recommended for visibility and the engine cooling. Then there are also general 3 types of descent. That is the glide, powered and cruise. So as a climb, opposite to is a glide. So descent, and in the descent we have the glide, and it is powered glide and the cruise glide. So these are the 3 glide conditions. There is a common misconception that in the climb the lift is increased. So it is not so. If you see here, just I will draw one aircraft and then we will see how these things are working. This is the aircraft, this is the wing, this is the tail, this is the and it is the climbing with some angle gamma. So if you see here, this is the lift, this is the velocity, and this is the weight. So for the cruise flight we are L is equal to W, but for this flight this L is equal to W cos gamma. So this value of cos gamma will be always lesser than this. So for the climb, this lift is greater than, lift required is less than the actual weight, and that is the depend upon the cos gamma. So this we have to understand that for the climb case, it is not necessary that this lift is higher than the this lift requirement is lesser than the cruise condition. Since if lift must equal to the weight in the level flight, it might appear logical that lift should be increased to climb, but it is not so. Drawing the forces to show that lift is not increased in the climb, but it is slightly reduced. Just now I have already shown you. So this we will see here, the forces acting on aeroplane in a climb. So here it is a relative airflow. This you can see. This means your aircraft is in this direction. Just I will draw the aircraft also. This is your aircraft and it is climbing in this. So relative airflow is in this direction. So it is shown here. So in the normal case, if you see in the if this is your gamma, so what will happen here? This drag, and here you have, this is here the weight. This is the perpendicular of the weight. So net, this forces will be your R1. So if you make this vector sum of D and the W, you will get R1 here. So this is the one condition. And if you see another here in the another diagram, if you see here, drag and the weight are combined. So if you see the net effect in this case, when aircraft is climbed, you have opposite to this thrust, you have the D plus W sine gamma. So this is your D, this weight component, this is a W sine gamma. So this thrust is equal to D plus W sine gamma. But if you see here in another diagram, what is the lift now? So here, if you see in this diagram, as per steady state, your thrust, this thing should be equal to drag. But it is this much, it is higher. Why higher? Because this weight of sine of gamma, weight sine of gamma is added. So your, this is extra. This much thrust we required extra for the climb. But what about lift? If I draw here, equal to this much will be there, and this is the gamma. So this velocity, this from here to here, this much will be W cos gamma. So this W cos gamma is less than the W. So lift required is less than the weight, and which is equal to W cos gamma, not sine gamma, W cos of gamma, where this is the gamma is a flight path angle. Gamma is flight path angle. So if you see here, this is the lift, and this is the this is the thrust. So we need a reaction which is R2, which is supposed to be equal to this. So in this way, these are the forces acting on the aircraft during climb. Since the airplane is in equilibrium, there must be a force equal and opposite to the resultant force R1 here. There should be one force. So we have drawn this another diagram equal to this R1 is equal to R2, and then we can find out this component. Then draw a line from the central point equal and opposite to R1 and label this as a R2 here. So we have made this as a R2 here. This is the R2. And if we make this component parallel and the perpendicular to this, so perpendicular is the lift and parallel to this is a thrust. And this thrust is more than the drag, but this lift is less than the weight during the climb. So if we resolve this force R2, it's have two component, lift and the thrust. So this is the lift here, L is equal to lift, and this is the here thrust. This is the thrust. In straight and level flight, thrust equal to drag. So what is the straight and the level flight? If aircraft is flying in such a way that there is no change in altitude, no change in altitude, no change in acceleration, and third one is no change in bank angle. This is no bank angle. So if we have this three condition, we can say that aircraft is in straight and level flight. In this case, thrust is equal to drag and lift is equal to weight, which we have already covered in our previous classes. But in climb, what happens? Thrust must increase to equal the drag plus the rearward component of the weight. So we have seen here, and I will draw again here. This is your aircraft. So this is the weight, this is the drag, this is the thrust, this is the lift. So here we can see that, and this is the gamma. So this thrust will be D plus W sine gamma. This thrust is equal to D plus W sine gamma, because this is the gamma, and one component which will be here W sine gamma will be adding to this D, and this has to be countered by the thrust. But if you see here, if it should be clear that in a steady climb, thrust is more than the drag. So here T is greater than drag, and how much? It is W sine gamma is greater than the drag. Why then does the aeroplane not accelerate? So if the thrust is higher than the drag, why this aircraft is not accelerating? To resolve this question, break weight down into its two component with the rearward component of the weight. So this is the rearward here, this one W sine gamma, and which is added to the vector D vector. So thrust is equal to the drag plus the RCW. So thrust is equal to W plus RCW, means rearward of the weight, and W plus here we can write that D plus W sine gamma. You may wish to finish off the parallelogram to tidy up your resolution of vector. The end results looks like figure 3 in the next slide. So this you can see in this slide. Very, very clear. This slide goes that this is your gamma here. It is climbing. This is the relative wind here. If you see here, initially the weight is here, this green line initially, but due to this drag and this yellow line will be the net drag. This net drag net drag is equal to drag plus RCW, rearward component of the weight, and here rearward is W sine of gamma. So this is this line R1, and this I can show you that this is the R1. Now if you see this, to counter this thing, we need to have thrust is equal to D plus RCW, and which is here this line, this is your thrust. So we got this line, and if you see here this R1, if you extend this same amount, R1 is equal to R2, this is equal to this. So, and you know this, so if you draw the parallelogram, you will get this lift. So how much lift is required for this? Lift is required, you can find out this using this parallelogram. So we can find out here that lift is equal to less than weight, because this weight is equal to, lift is equal to W1, and which is W cos of gamma. So this W1 is less than W. So for climb condition, we can see that this weight of the aircraft is, this lift of the aircraft is less than the weight, and here W1 which is shown is less than the actual weight of W. So this you can see here, this much variation is existing. So here the forces acting on an aeroplane in the climb condition is shown here. Now I will discuss about factors affecting the climb. So power. We have seen that as much you want the climb, your power requirement is high and high. So power R become higher as total drag is D plus W sine gamma. To counter this is called TR, D plus W sine gamma. So this sine gamma is higher, so we need more power to counter. The better climb performance will be there. Altitude, if you see here that engine performance, that is the power decreases with altitude. So as you go higher and higher, the engine power is decreasing. So there will be a limit to how high the airplane can fly. So how much you can fly? You cannot fly as per your choice. Altitude, there is a limited altitude, because your power available will be decreasing as you go higher and higher, and your power requirement, that is the drag of the aircraft, will be increasing as you go higher. So power available is increasing, power requirement is decreasing, so there is a limit. You cannot go beyond that limit. So weight is also very important, because just now you have seen that weight is everywhere. The greater the weight, the greater will be the RCW, that is the rearward components of the weight. Therefore, weight reduces the rate of climb and the angle. So the greater the weight, the greater will be the RCW, that is the rearward component of the weight. Therefore, weight reduces the rate of climb and the angle. Now we are using the flaps. Flaps are the lift producing devices. Additional lift is provided by the flap. So flap increases the lift and the drag and alter the lift to drag ratio. Since drag opposing the thrust, and increase in drag will reduce the rate and the angle of climb. So if you are using the flaps, it will increase the lift, also the drag. So L by D ratio will be altered. The drag is opposite to the thrust, so we need more thrust, and increase in drag will reduce the rate of climb and the angle of climb. Then wind is also very important factor. The direction of the wing is very important, affects the climb angle and the distance traveled over the ground, the range to reach a specific altitude. So wind is also very important for range of the aircraft. If it is the tailwind means if aircraft is moving forward, wind is coming from behind, then it is a tailwind, and if it is opposite, it is called headwind. If you want a high climb angle, if you want the more range, your favorable wind is from behind. It is called the tailwind. So if the wind is tailwind, it is favorable, and if it is the headwind, it is not favorable. Now we will see the most economical climb. What is the meaning of most economical climb? The climb that uses the smallest amount of fuel. So we have to select some velocity, some climb angle at which we are getting the minimum fuel consumption. That state is known as the most economical climb. We can see here that if we take as dW by dt minus CT, C is a specific fuel consumption and rate of change of weight. Now if you see here the dH by dt, that is climb rate, is equal to TV minus dV. TV is a power available, dV is a power required, divided by W. So this we have already seen, I think you remember. Now if you divide equation 1 by 2, then we will get dW, because this dt and this dt will be cancelled. So now dW by dH is equal to minus CTW divided by TV minus dV. I think it is very much clear. Now we can write that opposite, if you reverse this, dH by dW is equal to TV minus dV divided by minus C, T and W. So this is our third equation. So here a rate of change of altitude with respect to the weight, that is the derivative of dH dW is equal to TV minus dV by divided by minus CTW. TV is a power available, dV is equal to power required. So for most economical climb, we wish to maximize this value as, so dH by dW maximum is equal to TV minus dV maximum or minus CTW minimum. Fuel consumption should be minimum and this value should be maximum. There is a strong similarity between the fastest climb and the most economical climb, because for the fastest climb also we have the same thing. In both cases we need to maximize the excess power. So here TV minus dV is equal to power excess power, power excess. So for the fastest climb also we need the most highest power excess. For this case also power excess should be maximum. The fastest climb is almost the most economical climb. So if you are flying with the fastest climb, is also equal to most economical climb. Both are same. So this we have to take care of. Time to climb and fuel to climb. So now I will discuss how much time and how much fuel is required for that climb. This we are going to discuss in this topic, in this slide. So time rate of change of altitude, that is dH by dt. So this is called h dot, and this h dot is equal to dH by dt, and dH by dt is equal to rate of climb, and this rate of climb is equal to V sin gamma. Just I will give one demo for this. So it is assumed here, this is the velocity V, this is the VC, and this vertical velocity is called VC, and this VC is equal to rate of climb, and this is equal to V into, and this is the gamma, V into sine gamma. So this is here mentioned that rate of climb is equal to V sine gamma. Time dt required to gain the small height dh at a given instantaneous altitude is. So how much time is required? From here dt is equal to dh by h v. So we can see that dt is equal to dh divided by rate of climb, and this rate of climb is equal to dh divided by v sine of gamma. So time to climb from one altitude, that is h1, to another altitude h2 is obtained by integrating this equation. So we can see that time is equal to h1 to h2 dh by ROC, and here we can say h1 to h2 dh by v sine gamma. So the time to climb from sea level to any given altitude h is, so we can write that 0, this sea level is 0, 0 to h dh by v sine gamma is equal to 0 to h dh by rate of climb. So if rate of climb is maximum is used, so if you are using here rate of climb maximum, if ROC is maximum, so time t will be minimum. Then minimum time to climb is, so minimum time to climb is, we can write t minimum is equal to 0 to h dh by rate of climb maximum, 0 to h dh rate of v rate of climb maximum into sine gamma of rate of climb maximum. So here we can see that t time required minimum, t0 to h summation d delta h by v ROC maximum sine gamma of ROC maximum. So summation of t is equal to 0 to h delta h by rate of climb maximum for the gamma. If you are neglecting the gamma, so we will get here delta h by rate of climb maximum. So fuel to climb, this is the time to climb. So this is the time to climb. Now if I want fuel to climb, time to climb, now fuel mass to climb, how much fuel is required to climb this. So mass of fuel is equal to m, 0 to m ci ti by wi into delta h. Now if you want the distance to climb, so distance is equal to x rate of climb into delta t. So here 0 to h v c cos gamma l into delta t. So this is the ROC is equal to vi cos gamma I into delta t. So this is the maximum distance, and this is the fuel mass required. Now I will discuss about the ground effect on the aircraft. How the ground is, if the aircraft is flying near the ground, what will happen? Especially when you are landing and the takeoff. So if you are taking off from here and you are climbing like this, so up to here as you are leaving, you have some ground effect. And if you are landing, then also if you are landing from here, so as and when you are very near to the ground, there will be some effect on your aircraft that we are going to discuss what is going to happen. First, I will discuss about coefficient of lift versus alpha, then pitching moment, Cm versus alpha, what is happening in these two conditions. So, if you see here, in ground effect, and this is the out ground effect. So, if you see the CL maximum in ground effect, it is here. But if you see here, out of ground effect, CL is here. So, your CL maximum value is also high and stall angle also high. Stall angle high if you are away from the ground. But if you are near the ground, your stall angle is reduced. Stall angle is reduced and CL maximum also reduced. So you will get less CL maximum. So you have to speed up the aircraft to attain the same CL maximum. So this is the conclusion, that if you are in the ground effect, your CL maximum is also reduced, your stall angle is also reduced. So to have the same effect of CL, you should speed up the aircraft. But we don't want to speed up during landing. If you are speeding up, it will not be good. Now I will see about the CM. So if you see the CM out of ground effect and the in ground effect, and if you see here the in ground effect, your CM dCm by d alpha is less than dCm of d alpha of OGE, and this is the IGE, in ground effect, and this is the out ground effect. So this is the effect of the ground effect on the aircraft when you are flying near the runway. If you see another thing, that is CD versus alpha. So in ground effect, your CD is, for the same angle, if you see, the CD is here, and if you see for the same angle, CD is here. So in ground effect, your drag is reduced. Drag is reduced during ground effect. Okay, so here and here. So in ground effect, you are here. So for every case, your CD is more for out of ground, but if you are near the ground, your CD will be decreasing, and this CD will play a sufficient role for your landing performance. Now I will discuss about descending flight. Means, if I talk about the phases of the flight, so this is the takeoff, this is the climb, this is the cruise, if you see here, this is the descent here, loiter, and then it is landing. Okay, so these are the phases of the flight. So we are now here. We have discussed about the climb. Now we will be discussing about descent flight. So it is DESCEN, descending flight. This zone is the descending flight. So equilibrium is required for steady descent. If while in level flight, the power is removed, there will be no force balancing the drag. So I will just discuss about this plot, and this you can see that if your aircraft is going like this, what will happen? So if it is like this, relative airflow will be like this. This is your descent angle, gamma. So drag will act opposite to this, and there is a weight here. So the lift will act in this case. So in order to maintain flight speed, the nose must be lowered. So in this case, you have to lower the nose so that it will start falling down. With the nose lowered and weight still acting downwards on the center of the earth, there is now a forward component of the weight that balances the drag. So here we have a forward component of the weight is here, that is FCW. This FCW is balancing the drag. State that the equilibrium, there must be a force equal and opposite to the weight. So here FCW is equal to drag. Here thrust is not there. So now if you see, to counter this drag, we have this FCW. And if we resolve this and this, so this is the weight, we know, this we know, and we can draw this parallelogram. And if we extend this R, we know this drag, we can find out this lift. So how much lift is required for this, we can calculate. State that the equilibrium thrust must be force equal and opposite to the weight. This force R here, this is the force R, is made of lift and the drag. Therefore, the airplane is in equilibrium. So this you can see the figure here, which is mentioned here. Now, as previously I have discussed factors affecting the climb, there are some factors which are affecting the descent also. So here I have shown one diagram. So here we can see that the weight is here. It is descending. There will be a drag in this direction. Initially this is the lift, but it is the weight W, and this will generate some additional lift. So here the power, the more power used, the less the rate of descent. So if you want to reduce the drag, reduce the rate of descent, more power is required. Lift to drag ratio, it is a efficiency. The higher the lift to drag ratio, the further the airplane will glide, means range will be high. Weight is also very important parameter. An increase in weight will increase the FCW, increasing the speed down the slope and therefore the rate of descent, but not the descent angle. Rate of descent, an increase in weight will increase the front component of weight, FCW, increasing the speed down the slope and therefore the rate of descent, but not the descent angle. So rate of descent will decrease. Flaps, if you use the flaps, the increased drag produced by the flap requires an increased FCW to maintain the equilibrium and thereby steepens the descent, increases the rate of descent and reduces the range. So if you are using the flap, it is not good option. It increases the drag produced by the flap, requires an increase forward component of the weight to maintain equilibrium and thereby steepens the descent. So as you increase the flap, it will more descent will be there, more angle will be there. Wind affects only the descent angle and the range from a given altitude. Now I will discuss about the descent. Descending flight is the major flight operation prior to a landing. So before the landing, descending is very, very essential because your aircraft is at higher altitude. From there, it has to first come down to the lower altitude. It is the lowest cost flight because in this we have very minimum thrust required. So we are just only for starting case engine we are not switching off. However, a very 10 to 15% amount of only throttle we give. In it, aircraft decreases its altitude and is opposite to the climb. Descents are the essential component of an approach landing. Descending is very important. So if you see here, I have already shown you, this is the climb, this is the cruise, and this is the descent, and then this is the landing. So this is the descent. Here, aircraft has to come down. Descents are the essential component of any approach landing. Without this, you cannot land. For large aircraft and the long range aircraft, descents starts from 150 to 200 kilometers prior to the approach. So if it is a big aircraft like our Boeing, Airbus 320 and all, before 150 to 220 kilometers prior we start approaching, and pilot will announce that your destination is about to reach, and he starts descending the aircraft. Aircraft speed should decrease from cruise velocity to the approach velocity. Cruise is very high, somewhere it's 800 and 900 for Boeing and all, but for descent it may be 400, 500 kilometers per hour. Some essential descents are to avoid the traffic. So in which condition we have to make our aircraft to come down to avoid the traffic? Poor flight conditions, turbulence, icing, bad weather, etc. Clouds, to enter warmer air, to take advantage of the wind direction. Now we have to see what are the emergency descents. Sometimes some aircraft is coming, we have to see that. So sudden decompression below 10,000 feet forcing the descent. If your aircraft has high altitude 35,000 feet and you are feeling that there is less pressure in the cabin, pilot has to come down to 10,000 feet or 8,000 feet so that everyone will get the same pressure requirement. Decreases in engine power due to malfunction. If it is malfunctioning and it is not able to be in a climb in very high altitude, it has to come down. Decrease in lift due to control malfunction or wing icing. Increase in drag, air mass moving downwards, terrain induced downdraft, thunder storm and microburst. If these cases are there, you have to come down. Some facts of descents: that angle of descent is 3 to 5 degree. Pilot apply 10 to 30% of the power thrust to keep pitch altitude nose down with constant airspeed. In case of emergencies like fire or loss of cabin pressure, rapid descent is performed. Engine failure or unpowered descent is steeper than the normal flight. Space shuttle has descent angle of 21 degree at space. Engine tuned off descent is called the gliding flight. When descent angle is 90 degree, it is referred as a dive. So dive means it is like it is flying and it is 90 degree falling down. It is called the dive. And if engine is turned off, then we say that it is a glide flight. Now we will see the equation of motion for this descent flight. Based on the Newton's second law, in an unaccelerated descending flight, equilibrium of forces in x and z directions are this. We can see that Fz is equal to 0 and this is L minus W cos gamma. It is in the perpendicular to the velocity, this one, and this is the parallel to velocity. So Fz is equal to L minus W cos gamma is equal to 0, and in the x direction is equal to D minus T minus W sin gamma is equal to 0. This we have discussed earlier also. So here we can see here, these all the diagrams are here. x direction in this v direction is a x, and perpendicular to this it is lift. So this lift is equal to here w, and this is the gamma, so w cos gamma. So it is the first equation, and second one is in the direction of this. So here is a drag, and this is the weight component also. So this t has to counter. So this drag minus t minus w sine gamma. So this w will be in the same direction of the v. So here we can write that gamma is equal to cos inverse from this L is equal to w cos gamma. So cos gamma is equal to L by w. So gamma is equal to cos inverse L by w. So this is the value of gamma, and we know that at what we have the maximum value. If L by w is equal to same, so it is 1, cos 1 is equal to 0. So it is level flight. So the rate of descent ROD is defined as v sine gamma, that is the inverse that direction. For a typical deaccelerated descent, we need to include the deacceleration A in the governing equation. So we can write that Fz is equal to maz, L minus w cos gamma is equal to maz, and the x direction is equal to max, t plus w sine gamma minus d is equal to max, where ax is the deacceleration along the x-axis and az is the deacceleration along the z-axis, where ax is equal to v2 square minus v1 square by 2 into x. So this is the average acceleration. This is called the average acceleration. Ax is a average. Ax is average acceleration. Now, in the next lecture, I am going to discuss about these topics: effect of wind in aircraft performance, types of wind, headwind, tailwind, then ground velocity, range equation with ground velocity, effect of head and tailwind in fuel consumption, effect of head and tailwind for a jet aircraft. These are the references: Anderson JD, Aircraft Performance and Design, International Edition, McGraw-Hill's first edition, 1999. SL by ME, Aircraft Performance, Theory and Practice, AIA Education Series, AIAA. Any questions, you are welcome to ask. My email ID is yddwivedhi, dwivedhi @gmail.com. You are always welcome to ask any doubts, any question. If you feel that there is some mistake, I really pardon for that. And please do comments, like and subscribe this channel. Thank you very much for the joining. Be tuned for my next lecture. Till then, goodbye and see you.
Like, share and subscribe. Hit the bell icon for more updates.